In this video, I'm going to show you how to create a particle system that makes use of strange or chaotic attractors. These strange or chaotic attractors are systems of movement for particles that result in very cool, strange, unique individual patterns that are very chaotic on the micro level, meaning that these particles have very chaotic and bizarre movements, but they result in certain patterns or images or shapes on the macro level, as in when all of these particles come together. This can be used as the basis for a lot of cool visual and audio-visual creations, and we are going to be looking at what they are, how to implement them in MSP, and how to make sense of the mathematical formulas that result in these cool shapes. Let's begin. Alright, I want to do two things initially. I first want to create a visual output system, and then I want to figure out what these attractors are and how exactly are we going to approach this as we implement the system of attractors or chaotic attractors in Jitter. So let's start by creating a jit.world. I'm going to give this an arbitrary name such as attractive, so we know that this jit world is indeed attractive. And I'm going to give it some attributes as well, such as floating set to 1 and FSAA set to also 1. And here's a window. To make sure I can navigate this jit.world, I'm going to create a toggle connected to the first inlet, and I'm also going to create jit.fps GUI for that sweet FPS meter. And if I turn this toggle on, there we go, it is running. There is nothing interesting happening on the screen, but something is happening at the rate of 60 frames per second. And while that is happening, I am going to check out what these attractors are, because this is important, right? Attractors is a complicated system. It has to do with mathematics, it has to do with dynamical systems, but I believe it is still possible to understand how it functions without going too deep into the maths of it. So this is how Wikipedia describes it. An attractor is a set of states toward which a system tends to evolve for a wide variety of starting conditions of the system. Kind of meaning that if we have a certain space and if we have things such as particles or objects or shapes, and if we make them move according to certain mathematical formulas or logics, certain patterns are going to emerge, a certain set of states are going to emerge. And that set of states and that logic in which that set of states function is called an attractor, right? And if this evolving variable, a point or points or a curve or a manifold or any kind of geometrical shape is 2 or 3 dimensional, then the attractor of the dynamic process can be represented geometrically in 2 or 3 dimensions. That is what we want to do. We want to visualize an attractor system using 3 dimensions. Now, as I've said, this is a very in-depth topic, so I don't want to get into the maths of it and the mathematical definitions of it. We are going to be tackling on some mathematical formulas down the line, but I just want to point your attention to the concept of a strange attractor, because that's what we are going to be dealing with, and that is, in my opinion, the cooler part of attractors. So an attractor is called strange if it has a fractal structure, meaning that a strange attractor is usually chaotic and it will exhibit sensitive dependence on initial conditions. So any 2 arbitrarily close alternative initial points on the attractor after any of various numbers of iterations will lead to points that are arbitrarily far apart. Okay, this is a very vague statement, but here is what it essentially means. If I have a point here, it's going to move in a certain way, and over some amount of time it is going to resemble this pattern. However, if I have a point that is slightly farther or, closer, or, it's at a certain distance from that initial point, it is going to follow a completely different path. It's going to move and behave in a completely different manner. However, when we look at the macro level, when we zoom out and when we look at the emerging patterns, it is still going to be this pattern. And that is what is so cool about strange attractors, also called chaotic attractors. In the micro level, if we really zoom in and look at the movement of each particle, it is really random. It's very hard to predict and see how it evolves. However, when they're all together, really cool patterns start to emerge. Now, there is this really cool website that has a lot of formulas for attractors, all different kinds of attractors, certain visuals for attractors. It's called a 3dmeyer.de, and then something, something, something in German. However, what interests me here is this list. So I'm going to put this in the video description as well, so you can check out, I don't know, the Liu Chen attractor, look at this nice mass formula, which hopefully you'll be able to make sense of by the end of this video, then look at all of these cool images and try to recreate it on your own. However, I'm not that interested in the Liu Chen attractor because I already have my eyes set on a certain attractor called the Thomas attractor. Right, and this is how it is supposed to look based on different viewpoints, and here are the different signals or variations on the x, y, and z coordinates of a random given particle. All right, now the main meat is here. There is a very specific mathematical formula that we have to adapt to our points. So let's go back to Max MSP. Let's go back to our JIT.world system, and let's start by creating a bunch of random particles before we think about how we are going to make them move. So as always, I'm going to use JIT.gl mesh to visualize a bunch of points. Now I need to give it, or I should give it, the name of my context as an argument. So I'm also going to give it the argument of attractive. And then I'm going to go on by giving it the attribute draw_mode points. I can give it an initial color 1111, meaning it's going to be completely white, and I can give it a point_size, and let's make it, I don't know, 3. These are all parameters you yourself can change down the line. Now, JIT.gl mesh is going to expect jitter matrices for its data, right? So we can, for the initial starting point of our particles or points, use just random values. So I can use jit.noise to generate a random jitter matrix, or a jitter matrix with random contents. I can give this matrix 3 planes, meaning that each point is going to have 3 values associated with it. These are going to be interpreted as x, y, and z coordinates. The data type should be float 32, and then the dimension should be just the amount of particles we are going to have. So let's have, I don't know, 2,500 particles. All right, so this should go into the first inlet of JIT.gl mesh, and now if I send a bank, I should see something in this lovely window. And I do. Here we go. There are a bunch of particles. As you can see, they're kind of stuck on the top right quadrants of the screen, and that happens because jit.noise is giving us random values that go from 0 to 1, but our jit.world has 0 as the middle point, and it also expects us to go into negative values as well for the coordinates. A very easy way to fix this is to use the jit.map object, which is going to map input range to output range in a jitter matrix. To set these ranges, we have to use the map attribute and then just give it the values. So the incoming range of values go from 0 to 1, and we want to map these from -1 to 1. So if we put this right after JIT noise, so it gets processed and gets mapped and scaled accordingly, and then it goes into JIT.gl mesh, we should receive a bunch of nice random points. Also, to make sure we can navigate this 3D space in a nice and interesting manner for when we have implemented the attractor formula, let's set up a camera and some ways of navigating that camera. So I'm going to create a JIT.gl camera. Again, the context name needs to be the first argument, so attractive, and then I believe, and this is not going to change anything, but I believe I should be giving it some attributes as well. So first of all, look at 0, 0, 0. So it should always be staring at the center point of the camera, and then look should be set to 1. So it should be forced to always look at the 0 point. So we can kind of rotate around the 0 point and have a very nice visual effect. What I can also do is to use jit.gl, no, it should be jit.anim.drive with the attributes UI_listen set to 1. Now, if this object is connected to JIT.gl camera, after I click on my JIT world window, I should be able to look around by using the WASD keys and rotate by using the Q and Z buttons. Right, so now you can see I'm zooming out, I'm zooming in, I'm rotating, so I can really view this collection of points in any way that I want. If I ever want to reset the position of the camera, I can simply send it the message. Let me see if I remember this correctly. anim_reset. That message should go to both of these objects, and if I click this, There we go. We are back at the beginning. So to sum this up, we have created a bunch of random points. These are not moving in any meaningful fashion yet, and we have created a camera system that we can control by using the arrow keys, the WASD keys, and it's also possible to reset it by using this specific message. Moving on. Now let's go back to the web page. Let's look at this strange formula and let's try to decipher this. Now, first of all, most attractors, most chaotic attractors, most system of strange attractors have constants, right? In this case, there is a single constant. This constant is called B for some reason. I'm sure there is some reason this constant is called B. I don't know what it is or why it's called B at this point. I just know that its default value is 0.19 and it should stay that way, and this is a constant or a parameter that we can change down the line. Apart from that, there is a certain mathematical formula described here, and I can try to maybe zoom in a bit so this fills the screen as I'm talking about it. There we go. All right, now there are in fact 3 formulas here, and each of these formulas is defining how a particle should behave or move on a given axis, more specifically on the x-axis, on the y-axis, and on the z-axis. This dx stands for delta x. This is giving us how much the particle needs to move on the x-axis. Should it move forward? Should it move backward? Should it stay where it is? Same thing with the y-axis and same thing with the z-axis. So these formulas, these calculations are not giving us the next state, the next position of the particle. They are just giving us in which way those particles should move from their current points. I'm going to ignore this dt for now, so let's just imagine that this is dx equals minus b times x plus the sine of y. Now, as most cool mathematics tends to be, there are no numbers here, but there are a lot of cool symbols, and actually we do know a bunch of these symbols already. We know what x, y, and z is. They are the current states of our particles, right? So for any given particle, we have an x value, a y value, and a z value. We know that sine is a function or an operation that we can perform on a number. This is very easy to do, very intuitive in jitter and JIT-gen. We are going to get to that in a second. And we know that b is a constant. Right now it's 0.19. It can be anything really, but it is something that is defined. Meaning, if I want to figure out the delta of x, how much or in which way x is going to move, I just have to take minus b, so the negative equivalent of b, multiplied by x, and then I need to take the sine of y, and then I need to add those two values together, and there I have my delta x. Now, this goes for the other components as well. Delta y equals minus b times y plus the sine of z, and the delta z equals minus b times z plus the sine of x. To make this easier on all of us, I'm first going to translate this into a comment box in Max, and then I'm going to go on from there. So dx equals minus bx plus sine of y, dy equals minus b times y plus sine of z, and dz equals minus b times z plus sine of x. Now this here is a recursive thing, right? As in, I'm supposed to figure out the delta of my particle. I'm going to add that to the current state of the particle, and then I'm going to do it again. And then I'm going to do it again, and then I'm going to do it again as many times as I want. So we are talking about recursion. We are talking about feedback regarding the positions of these particles. Meaning I need two things. First of all, I need my good old friend JIT-gen to implement this specific formula. But second of all, I need some kind of recursion, or, well, maybe not recursion, maybe that is not the right word. I need a feedback system to make this work. And for this, I can use a named jitter matrix. So if I create a jit.matrix and I just give it a name as the first argument, pos, particle positions. I can put this right after jit.map. So the random particle positions go into this named jitter matrix. I don't need to define the amount of the data type, the dimensions, and how many planes this matrix has, because it's just going to adapt to whatever's coming in. The important thing is that this jitter matrix has a name, meaning if I create another jitter matrix, also with the name pos, changing one is going to change the other. So I can put this after JIT-gen, meaning I have the random positions of my particles in this part pass. They go through this formula, and that goes into jit.matrix part pass again, meaning that this one here has its contents updated as well. So if I trigger this again, it is going to go through JitGen again. It is again going to change part pass, meaning that the initial one is going to be changed as well. So each time I trigger part pass, it is going to initiate this feedback loop without breaking my computer or setting it on fire, which I always consider to be a plus. All right, now I believe nothing is going to happen if I click this button, right? The setting is correct, the objects are correct, the way they are connected is also correct. What is not correct is the contents of this JitGen right here. So I'm going to copy this formula, I'm going to go into JitGen, and now it is time to actually implement this formula. So I'm going to delete into here. I'm going to zoom in a bit so it's a bit more visible what is taking place. And I'm going to start by taking this input, right? So this is going to be every cell. This is going to be a process that is going to be the same for each cell in my matrix or each particle in my particle system. And this in1 is going to give me the position of each particle as 3 values, x, y, and z values. So the first thing I should do should be to take them apart. Swiss x, Swiss y, and Swiss z. There we go. All right. And eventually I'm going to apply this algorithm. For now, just imagine that this comment box is a very cool algorithm. And after this, I should pack these values back together, right? Because for the outputs, I want a single 3D vector. I want the x, y, and z positions as a single vector, as a single unit. There we go. Now I can start by calculating the new x position. And for that, I need to figure out the delta of x, right? And what was that? Well, it was minus b times x. So we need to define our constant b. If I remember right, that constant should be 0.90. Now we can do this by declaring a parameter in JitGen. So I just create a new object or operator, type in param, space, and then the name of the parameter. In this case, it's b, and then the default value, which is 0.90. Now, the cool trick I can do in JitGen is to refer to this name b as an argument, right? So since I have to take minus b and multiply it by x, what I can do is I can take Swiss x, I can create an object and just say multiply minus b. This wouldn't work in regular max MSP, right? If you ever tried this, you know that this will not work. However, in JitGen, in the world of Gen, this is going to work. The Gen language is going to know what we exactly mean when we type in minus b. We do mean this parameter's minus equivalent. All right, so x times minus b, and then we have to get the sign of y. That is very easy to do. We just have to create the sign object and take our y components, put it in the inlet, and there we go. And then we have to add these values together. Fairly simple. There we go. Of course, there is one more step. We know that this is the delta of x, so we should take our current x and we should add this delta x to the original position. So I'm going to create another plus object and take the original x, put it in here like this, and there we go. This is our new x position. Now, it's going to be the same for the y and the z positions. It's just the parameters that are different, right? For example, to figure out delta y, I have to multiply y by minus b, and then I have to get the sign of z, and I have to add those two together. So it's not so different. And just like before, I'm going to get y itself. Let's see if I can make this look all cool and professional like this. Fantastic. And this is going to be my y component. And finally, I'm going to multiply z by minus b. I'm going to get the sign of x. So I have to kind of reach out here. I'm going to add these together, and then the result, the delta, is going to be added to the z position. There we go, and this is going to be the z components. Okay, now there is one concept I have been consistently ignoring, and it is this dt. something we can translate as delta time, or the amount of time that is passing, because we need to have a way to figure out how much time is passing, how big is each step, and this is what this dt right here means. So each time we get the delta value of something, we should multiply or divide it by a dt value in such a way that it's going to give us a larger or smaller step size. Right, so I can create another param. I can give it the name dt, and I'm going to initially give this a very low value, like 0.001 or something like that. Again, if it doesn't exactly make sense to you what this dt means, you're going to see it in action hopefully in a second, and then it's going to make a bit more sense to you, I hope at least. Okay, so what we have to do then is to multiply the dx and dy and dz by this dt, which is again very easy to do in Gen, right? I can just type in multiply and then dt. Insert it here, same thing here, same thing here. Though I believe this is incorrect, because now I am multiplying the final result of my movement. So after adding it to the exposition by dt, I should not be doing it like that. So the multiplication by dt should happen right after we calculate dx, right? We have the two values here, we add them together, then we multiply this value by dt, and then we add it to our original exposition. I'm going to do the same thing here. And guess what? I'm going to do the same thing here as well. Okay, so this should be the implementation of our chaotic attractor. So let's see if this works. How are we going to see if this works? Well, first of all, I'm going to save this patch in case it crashes, because I'm a bit paranoid like that. And secondly, I'm first going to send a bank to jit.noise to generate a bunch of new particles at random positions. And now to trigger the system, I have to send a bank to my particle position matrix, as in this specific part pos jitter matrix. You can see each time I click it, it moves ever so slightly, but my fingers aren't that strong, so something I can do is to take the second outlet of jit.world, which is going to send a bank each time a frame is rendered. So if this is 68 frames per second, I'm going to get 60 banks per second here, and simply make that the input of our particle position jitter matrix. Okay, and there we go. There is some movement. So these particles are moving in a certain way. They are very slow. And remember, this is what dt is, the amount of steps we are going to take over time. So the lower the dt value is in the specific application of the system, the slower this particle system is going to move. So when the patch is unlocked, I can right-click the first inlet of JitGen, choose dt, and then slightly raise this value. And look at this, there's a certain pattern emerging. Wow, this is really beautiful. Look at this. Okay, and here is our chaotic attractor. Now, the more I increase dt, the faster it's going to move. The faster it moves, the less definition it has. So if I go too fast, you're going to see it change form. Now it just looks like a line. There is not enough time for the particles to, I don't know, have more individuality, I imagine. But if I make it slower and slower, I can even go into negative values, and this is something really interesting. If I go into negative values, the particle cloud just dissipates. They just move in the opposite direction and they disappear off the screen. But then if I increase dt, if I go back to a positive value, they kind of come back together and reform the chaotic attractor. Now, another cool thing we can do is to play with this constant b, right? By default, this was 0.19, but this can be anything else, of course. So again, if I unlock the patch, if I right-click on the inlet of JitGen and then choose b, I receive this nice UI object that lets me edit the value of b. And look what happens as I'm increasing b, the shape itself is changing. If I lower b, it should go back to how it was before. It even has a certain movement to it. Look at this. This kind of chaotic behavior really reminds me of, I don't know, jellyfish or something. And I can make it go even lower and lower, and I'm going to get different patterns, different 3D patterns as I'm playing around with these two values. So these two, for instance, can be not only a system of visualization, but they can also be connected to something musical, for instance, right? They can control the playback of something, or they can be mapped to some parameters on synthesizers in order to create a very simple audiovisual experience using these strange attractors as basis. Now, one thing to watch out is to make sure that you do not break your chaotic attractors by messing with these constants too much. As in, if I go to, I don't know, a negative value but b, they're going to dissipate. And if I raise them again, they're going to come back, but then they're going to have this strange form. And sometimes it happens that if you mess with these values too much, you irreparably damage the particle system. So no matter what you do, it's not going to come back. Let me set this back to a normal value. See, for example, it's not back. Maybe it's going to come back in 10 minutes after all the particles are guided into their right positions. But if that happens, something simple and easy we can do would be to click this button that would send a bank digit noise, and this would reset the particle positions. And then we are back again with our strange attractor. So there you have it, a lot of possibilities, almost infinite possibilities of different patterns and shapes and sizes, which you can further customize by playing around with this JIT-GL mesh object. Let's make this a bit more attractive. There we go, so you can change the color or the draw mode, or you can get into point mode. You can lower or heighten the point size, so we can have smaller points and it looks a bit more slick, I believe. And you can use this as the basis for a lot of cool visual creations. So I hope you have a lot of fun with this, and thank you for watching.